Hello everyone. I welcome you all to the lecture series of alcohols, phenols and ethers. And in just previous lecture we had been discussing about chemical properties of alcohols, phenols and ethers. So among these chemical properties we have discussed regarding the ROH bond cleavage. There we have discussed the reaction of alcohols with sodium, reaction of alcohols with NaOH, and the esterification reaction and the acidic nature of alcohols. And then we have discussed the reaction involving ROH bond cleavage. There we have discussed the esterification, there we have discussed about the formation reaction of ROH with PCl3, PCl5, SOCl2, HCl in the presence of ZnCl2, and the dehydration reaction. So the dehydration reaction and its mechanism that we have discussed in our previous lecture to here. Okay, so now we will be proceeding further with other different properties of alcohols, phenols and ethers. So here we will be considering oxidation of alcohols. So let's mention oxidation of alcohols. So see, the alcohol can be primary, secondary or tertiary. So if the alcohol is primary alcohol, if the alcohol is primary alcohol, then on oxidation it will get oxidized to aldehyde. Aldehyde on oxidation will yield carboxylic acid, and if it's a secondary alcohol, then it on oxidation will yield ketone, and ketones also on oxidation, on some vigorous oxidation, yield carboxylic acid. Ketones, the oxidation of ketones is quite difficult as compared to the aldehydes. Okay, this property we also will use to distinguish in between them. Okay, so for this conversion we can use KMnO4 in the presence of OH negative. That's something known as Bayer's reagent. What is Bayer's reagent? That's basically called dilute alkaline KMnO4. Next to this is KMnO4 in the presence of H plus. Either KMnO4 in acidic medium also we can use, or K2Cr2O7 in the presence of H plus, or we can use concentrated HNO3. These we can use here. Uh, but these oxidizing agents are very strong oxidizing agent. If we will oxidize primary alcohol using KMnO4 in the H plus, KMnO4 in the presence of H plus or OH minus, it will oxidize it directly to carboxylic acid. It will not stop anywhere in between the aldehyde. So if we have to oxidize the alcohol up to aldehydes only, what we have to use is a mild oxidizing agent, and that's we have as PCC. We call it pyridinium chlorochromate, and it's pyridine, chlorine, and CrO3 in 1:1:1. That's known as pyridinium chlorochromate. And if it's primary alcohol, RCH2OH, it will be simply oxidized to RCHO. That is it. Okay. In case of tertiary alcohol, I have not discussed with you. And if it's secondary alcohol, say, let's mention step by step. Let's move. Okay. For the primary, if it's secondary, and then tertiary. So it will give you ketone. If it's tertiary alcohol, it will yield you alkene instead of an oxidized product. You will get an product by the process of elimination. So what you will get here is the alkene. So tertiary alcohols on oxidation, on vigorous oxidation, also yields alkenes. Okay, let's move ahead to next thing, that is catalytic dehydrogenation of alcohols. Catalytic dehydrogenation. These methods we will also study again in the preparation of aldehydes and ketones. Okay. So what is catalytic dehydrogenation? It's simply the alcohol is heated in presence of some metal like copper at 573 Kelvin, very high temperature, and it will yield you aldehyde. Okay, and if it's a secondary alcohol, say, if it's a secondary alcohol, what it will yield you? It will give you ketone. Other oxidizing agents, na, like Fehling solution, Tollens reagent, that all we will discuss with aldehydes, ketones. Okay, we have briefed our discussion here because we are studying the chemical properties of alcohols. So next to this is, if it's tertiary alcohol, then instead of dehydrogenation, what occurs here is the dehydration. So dehydration occurs only in case of primary and secondary alcohol. Dehydrogenation. So hydrogen is formed as a byproduct here in case of primary and secondary alcohol, while the H2O is formed as a byproduct here in case of tertiary alcohol. So again, it's alkene formed in case of tertiary alcohol. Let us discuss a few chemical reactions of phenol also. A lot we have discussed about alcohols. So let's move ahead to chemical reactions of phenol. So there are various reaction of phenols: nitration, halogenation, Colway's reaction, Riemann reaction, reaction with zinc dust, formation of quinone. That all we will be discussing here. So let's begin with something that's nitration. So nitration on the basis of, if you are using dilute HNO3 here now, then it will give you a different product. And if you will use concentrated HNO3 in the presence of concentrated H2SO4, it will give you a different product. So the electrophile here is definitely NO2 positive only, that will get substituted at ortho and para position in both the cases. But in case of dilute HNO3, there is not much amount of NO2 positive produced, so it is simply getting substituted at ortho and para position. So what's happening there in case of para nitrophenol? It's forming picric acid here. That's 2,4,5 trinitrophenol. So various questions can be asked from here, like how can you separate ortho and para isomers? Why the ortho and para nitrophenol? Why ortho and para nitrophenol can be separated by steam distillation, or it can mention a simple statement like ortho and para nitrophenol can be separated by steam distillation. Comment. Yeah. So suppose it have asked why ortho and para nitrophenol can be separated by steam distillation. So what will be our answer is because of difference in their boiling points. Orthonitrophenol is having intramolecular hydrogen bonding while paranitrophenol is having intermolecular hydrogen bonding. So intramolecular hydrogen bonding is something which is decreasing the boiling point. Instead, intermolecular hydrogen bonding is something which is increasing the boiling point. So the in case of intramolecular hydrogen bonding, the boiling point is decreased somewhat, and in case of intermolecular hydrogen bonding, the boiling point is increased. So they are having different boiling points, so it's easier to separate them with the help of steam distillation. Next can be asked is why is the orthonitrophenol is less acidic as compared to paranitrophenol. So that again the reason is hydrogen bonding, intramolecular hydrogen bonding, same reason we will have. Second one is halogenation. This halogenation is also used as a distinguished test for phenols. If we will react phenol with Br2, so what it forms is tribromophenol. This is also called as bromine water test. Bromine water test. So this is a characteristic reaction of phenol. Or we can say this is a one of the distinguished test of phenols. However, aniline also gives this reaction. This is a distinguished test for phenol. Okay, we can distinguish phenols from rest of the compounds by this method. Okay. Next to this is if we don't want bromine to get substituted on all the three positions, we just want orthobromophenol and parabromophenol. So what to do in that case? What we will do in that case is we will use a non-polar solvent here so that less of Br positive will be generated. Here the polarity of phenol is responsible for generation of electrophile, that is Br positive. Okay, so Br2 is a non-polar molecule, but the polarity of phenol helps in generation of Br positive, and if we will non use a non-polar solvent, it will be generated in a less amount, and ortho and para bromophenol will be formed here, and definitely para will be a major product because being more symmetric. Okay, so CS2, a non-polar solvent you have to use here. Next is Colway's reaction, third one. So we have studied two reactions till now, nitration and halogenation. Both are having a few specific points among them. Okay. Next to this is Colway's reaction. It's phenol getting reacted with NaOH in the presence of CO2, followed by reaction with H2O, and it gives you orthosalicylic acid and okay. Next to this is the Riemer-Tiemann reaction. That's about Kolbe's reaction, that phenol when reacted with NaOH in the presence of CO2 and H2O, it will yield you orthosalicylic acid and parasalicylic acid. Next is Riemer-Tiemann reaction. So when Riemer-Tiemann reaction is there, this is the only reaction in our syllabus in which the attacking reagent is dichlorocarbon. Otherwise, we have always observed only attacking species as electrophiles, nucleophiles. So if it's a CHCl3 chloroform, then what is formed is salicylaldehyde, and if it's CCl4 carbon tetrachloride, then what is formed is salicylic acid. So simply how the dichlorocarbon is formed here. First of all, though, let us have a look at that thing. See, CHCl3 chloroform reacts with KOH to form CCl2 plus KCl plus H2O. This is carbon and two chlorine atoms are there. So this will be called as dichlorocarbon because two Cl atoms are there. So that's about the formation of dichlorocarbon. Now, this dichlorocarbon is an electron deficient species. So it will just behave like electrophile. So this dichlorocarbon will attack on ortho and para positions of phenol, and the ring will lose its aromaticity for an instance. It's just like this. Okay. And then again ring will gain its aromaticity by losing one H plus from here. Okay. And which is further hydrolyzed to form salicylic. As we know, in generally two OH groups on the same carbon atom are unstable, so they will just one water molecule will be removed and that will form double bond O. In this way. I hope you understood this. So what is formed here is the uh, salicylic. If it's a CCl4, then what is formed is the salicylic acid. And one more thing we can also mention here, that's the formation of aspirin drug. Next is the formation of aspirin drug. That is when salicylic acid is acetylized, then what is formed is aspirin. This is known as aspirin. So this is just an esterification reaction, kind of that ester is formed here. Next to this is reduction and oxidation of phenol or reaction. Fifth is reduction and sixth is oxidation. Reduction of phenol will give you benzene. It's just giving us benzene plus ZNO. And then oxidation of phenol gives us benzoquinone. Next is commercial importance of alcohols. So this is quinona, similar to quinol. So next is commercial importance. Uh, if we will talk about commercial importance of alcohols, then what comes is to our mind is ethanol, uh, because it is maximum used as alcoholic beverage and is sold in large amount. So before that there comes methanol. These are the chemical reactions given in the NCRT textbook. Okay. So this is the atmospheric pressure we have to give. Sorry. This is the pressure we have to give, 200 to 300 atm, and the temperature will be like 573 Kelvin to 673 Kelvin. Okay, and this will form methanol. This methanol is highly poisonous. and it can cause blindness, and it is also used in paints. What happens with methanol is it get oxidized to methanaldehyde or methanoic acid in our brain, and which just harms our central nervous system and the other different organs. So what we can do with the methanol is just so methanol here is having various harmful effects on our health. Sometimes it is also formed along with ethanol if prepared, if the ethanol if the as an alcoholic drink is prepared in homes at very small scale, so it gets synthesized in very small amount in that case, methanol. So in that case what is done is uh, a large amount of ethanol is given to that person so that his kidneys can excrete the excess amount of methanol out of his body. So that's also one of the point regarding methanol. How can we prepare ethanol? That's using sucrose. It will form C6H12O6 plus C6H12O6. Glucose and fructose. It will form, and which will further react with Zymase enzyme to form C2H5OH plus 2CO2. So that's how ethanol is prepared industrially. So that was regarding today's lecture. So what we have discussed in this lecture is the oxidation of phenols, catalytic dehydrogenation, chemical reactions of phenol, and commercial importance. So I have just mentioned the chemical reactions which were given in the NCRT textbook in the name of commercial importance of alcohols. Okay. Rest, we have discussed all these things many times. Also, we studied in our earlier classes also. Okay. Um so let's limit our discussion for this lecture up to here only. From the next lecture, we will begin with ethers. So thanks for watching the video. Have a good day. Bye bye.